Alright, 8.5 talks about areas in polar coordinates. What we're trying to do, we're trying to find an area of r equal f of theta. And there are two types of these areas that we look at. One, let me redraw this really quick. There. So if I run r from theta equal alpha to theta equal beta, and the desired area happened to be one of those. Unlike rectangular coordinates, we move left and right, up and down, north, south, east, west. If we look at this, we're trying to figure out how do you find the area, but that right there is not a straight line. So that reminds us of the area of a sector from polar coordinates, if you recall. If this is r, and the area of a sector where the central angle theta is centered at the origin, then the area that I'm desiring really is 1/2 r squared theta. Now, that's the area of a sector, but here we have variation. Those are varying. So what we do, we draw an arrow. Just like in rectangular coordinates, if you recall, we drew a rectangle, we call that delta x, top minus bottom. Here we draw an arrow. And unlike rectangular, polar is always the tip of the arrow minus the base of the arrow, just like here it is the top minus bottom. And if I call that theta sub I, then a sub I would be 1/2 r sub I squared times theta sub I squared. Well, if I want to find the area of that sector, I would integrate from alpha, the beginning, to the terminal beta of 1/2 r squared d theta. What's the catch? Theta must be in radians, if you recall. This formula doesn't work if you pick theta to be in degrees. And if I happen to come across two functions, if I'm looking at the area between two functions, kind of like what we did with x and y as well, what we do, we draw the arrow. And this is how it works. We take the area to equal the area of the desired region, to be the integral. It's still from whatever this angle is to still whatever this angle is, and 1/2, I could factor the 1/2 out of the tip, calling this r equal f of theta. So the tip of the arrow minus the base of the arrow. And that's how it works. Kind of like when we did back in the days when we had two of these functions and we said, oh, you take the top minus the bottom. Here you take the tip of the arrow, r sub 1, r sub 2. And that's how it works. And do recall that r is f of theta anyways. So, I start off with a couple of examples. First example, actually I have a lot of examples, not a couple of examples, a lot of those. Let me get my polar grid ready. So, I would look at r equal 3. I know it's a circle with a radius of 3. And I want the area between theta equal pi over 6. Pi over 6 is right there. And theta equal pi over 2. So pretty much what I'm doing, I'm looking for literally this area. I could use the area of a sector. I could say the area is 1/2 r squared, we know r is 3, times the angle. If I run from pi over 6 to pi over 2, the actual angle will be pi over 2 minus pi over 6, which all over 6, that would be 2 pi over 6, which is pi over 3. Oops. And that would be my area, or I could say area equals the integral, start with pi over 6, and at pi over 2 of 1/2 r squared d theta. And as you see, this is going to be 1/2 times 3 squared times theta evaluated from pi over 6 to pi over 2, which is literally that. So if it's that simple, you really don't need calculus. Now, on those, I'm going to set up all of these problems. I'm going to set up and you should expect me to do that on most of these problems as well on the exam. Here, I'm running theta between pi over 4, 45 degrees, and pi over 2. So I'm running theta between those, but I need to know what this graph looked like. I did deal with this already. That's pi equal 3, 1, 2, 3. If I draw y equal 3, which is the graph of this, there. I'm looking for this area. That's a triangle. You could use the area of a triangle. You could say, forget that. That's the area from pi over 4 with respect to theta to pi over 2. So that's theta equal to theta equal 1/2. And how does it go? If I run my arrow, do you see where the arrow runs to? The purple. What's the purple? It is 3 the cosecant of theta squared. Again, it's up to you. I say find the area, it's up to you. But, of course, you should know. Pretty soon that's not going to be the case. But I'm covering my bases and making sure that we cover every possible scenario you can think of. And how about this problem? Well, here, I'm looking at a circle wrapped around the positive x-axis with a diameter of 3, if you remember how that looked like. The quicker you get used to those, the better off you are, because graphing those is the beginning. And here we are. What do I want? I want the area of this. Now here you gotta start being careful. This is not as simple anymore. That is the area of a circle. Of course, you could write that, but we're gonna be using integration and things are gonna get a bit messier. So let me show you how this works. If I draw my arrow, I notice the arrow is running from the origin to this circle. So area equals the integral. If I run from 0 to pi over 2 of 1/2 3 the cosine of theta d theta, that gives me half of the area. And if I multiply that by 2, that gives me the bottom half. And that's how we're going to do most of these problems. Set up, do not solve. That's all you have to do for me. And let's get to the next problem. I need 3 of those circles. I don't need all of those. So let me get rid of one of those. Here we go. Much better. And if I take this, let's see. If I take this, and again, the graph is really half of the problem. This is, if you recall how this works, this is a 4-leaf graph. I want the area that encloses, or the area of one loop. I could ask for anything. Well, we know how that goes. 1, 2, 3, and -1, -2, -3. A graph of a sine wave starts at the origin, goes up to the amplitude, back down. Okay, that didn't work well. Let's make it back to there. So all what I need to know, this is 2 pi over 2, which is pi. This is half of it. This is half of it. Pi over 4, which means I need the pi over 4s. I am using a color that's hard to see. That's just for reference. My graph starts at 0, increases. By the time I hit pi over 2, I am at 3. There's pi over 4. 1, 2, 3. So there it is. Now I know these graphs are symmetric. Since I have 4 of those, I know they're 2 pi over 4 apart. So wherever this peaks, add 2 pi over 4. And those are my 4. Now, you're going to run into trouble if you're going to say 0 to 2 pi, because if you remember, we got to trace the whole graph before that on the previous problems. So the way we get around it here, we say, look, let's take area to equal. Let's find if I run from 0, the area, the desired area that I want is really the area this encloses. That will be those 4 pieces. But I know because of symmetry, if I start tracing from 0, and I notice the arrow is running just to the actual curve, to pi over 4, I know that's pi over 4, of 1/2 r squared d theta. What's r? It's right there. It's 3 the sine of 2 theta. And how many pieces I have? 1, 2, 3, 4, 5, 6, 7, 8. So this analogy is a must. 0 to 2 pi doesn't work. You get more or less of the area that you desire. That's not how we do this. So we're going to use symmetry all throughout. This problem, this is a 3-leaved graph. I'm going to enlarge that a bit. And I know how this works. I just need one of those leaves or petals. If you recall, we go up 1, 2, let's say 2, 4, and 2, 4 down. Again, since I know what the graph looks like, a graph of a cosine wave looks like this. R equal 4, R equal -4. 2 pi over 3, half of that is pi over 6. I'm sorry, pi over 3. And half of that is pi over 6. So that tells me what I need. I need the pi over 6's. Let me label those. Again, rough graph. It doesn't have to be exact. So I need the pi over 6's. These are all the pi over 6's. Remember, pi over 3 is 2 pi over 6. So here, I ignore the pi over 4's. And let me see how this works. At 0, I am at 4. At 0, I am at 1, 2, 3, 4. This decreases. By the time I reach pi over 6, I am at 0. Pretty much I'm done. And how's that? Well, I know that this is a 3-leafed graph. So they're 2 pi over 3 apart. Since this peaks at 0, the next one would be 2 pi over 3. The next one would be at, let me double check. Yeah. I'm sorry, 2 pi over 3. This is pi over 3. So 2 pi over 3 apart. Since this is 0, if you add 2 pi over 3, you're right there. And if you add another 2 pi over 3, you're right there. And another 2 pi over 3, you're right there. So the graph looks like this. I want to find the graph of those. And again, 0 to 2 pi will get you no credit whatsoever. None of these problems work out to be 0 to 2 pi. Only 1 or 2 out of everything we're going to do. And we're going to do tons of those. So if I look at the desired area, I'm going to integrate, and let's see how that works. Leave some space because we know we're going to use symmetry. I'm going to run from 0 to pi over 6. That takes care of all of it. And I'm running to the function. What is the function? For the cosine of 3 theta squared d theta. How many pieces? 1, 2, 3, 4, 5, 6 times that will get me what I want. If they say the area of one petal, you multiply by 2, and so on and so forth. I'll continue this in the next video.